Hey, Harsh here. Today we are going to talk about OSI model. So what exactly is OSI? It stands for Open Systems Interconnection. Think of it as a universal language or grammar for computers. Just like you need rules to write a letter so that post office can deliver it, computer need rules to move zeros and ones. The model breaks networking down into 7 distinct layers. Why 7? Because it separates concerns. The people building your web browser at layer 7 don't need to worry about the voltage levels in your Ethernet cable layer 1. It allows for interoperability, meaning a Mac can talk to a PC or a phone can talk to a server because they all agree on these rules. You're going to need to memorize this order, whether it's just for an interview or just sounding smart. We number them from bottom to top through 1 to 7. A popular way to remember this top down is all people seem to need data processing. But if you want to prefer bottom up, please do not throw sausage pizza away. Both work perfectly. Remember, the top layers are closest to you, the user, and the bottom layers are the closest to the hardware. Now, for my Indian audience, I found a very cool acronym on Gate Smashers as well. It was आज फिर से test नहीं देना पड़ेगा. So, आज is application layer, फिर is presentation layer, say is session layer, test is transport layer, nahi is network layer, dena is data link layer, and badega is physical layer. Thanks to Gate Smashers. Here's where it gets interesting. You send a message. Your data doesn't just fly across the wire as it is. It goes through a process called encapsulation. It's a set of Russian dolls. At level 7, it's just data. As it moves to layer 4, we add a header and call it a segment. At layer 3, we add an IP header and call it a packet. At layer 2, we add a MAC header and a footer, calling it a frame. Finally, at layer 1, it's just all raw bits. When the receiving computer gets it, it does the reverse, stripping off the headers layer by layer until it gets to the payload. This is called decapsulation. Let's start at the bottom. Layer 1 is the physical layer. This is the only layer that physically touches the real world. We aren't dealing with the logical data here, we are dealing with physics. Electricity on copper, pulses of light and fiber optics, or radio waves for Wi-Fi. If you have a layer 1 problem, it usually means a cable is unplugged or cut. Devices like hubs operate there. They are dumb devices that just repeat the electrical signals to everyone without looking at the data. Moving up to layer 2, the data link layer, this is responsible for hop-to-hop delivery. We take those raw bytes and organize them into frames. The currency of this layer is the MAC address. Every network card has a unique MAC address burned in by the manufacturer. Your switch also lives here. A switch is a smarter version of hub. It reads the MAC address and sends the frame only to the specific device that needs it. Note, this layer is strictly for local network. Layer 2 doesn't know about the internet. It only knows about the devices plugged into the same switch as you. Now we hit the big time. It is layer 3, the network layer. If layer 2 is about getting the data across the room, layer 3 is about getting your data across the world. This layer is responsible for end-to-end delivery. We use IP addresses here. Unlike MAC address, IP address are logical. They can change depending on where you are connected. The router is the king of layer 3. It looks at the destination IP on the packet and decides the best path to get there. Kind of like a GPS, finding the best and the fastest route through the traffic. Why do we need two addresses? Think of it like this. If IP address is the final address on the envelope, it tells you the letter is going 10 Downing Street. It stays the same the whole journey. The MAC address is like a truck that carries the letter. The letter moves from a mail truck, Mac A, to a plane, Mac B, to a delivery van, Mac C. The vehicle changes at every hop, but the destination IP never changes. Also, how do we find a MAC address if we only have an IP address? We use a protocol called ARP. It literally shouts to the local network who has this IP, and the device replies with, I do. Here is my MAC address. ARP is also Address resolution protocol. I forgot to mention the full form. Your computer is receiving billions of zeros and ones. How does it know which one belongs to your Spotify music and which one belongs to the email you are downloading? This is layer 4. Layer 4 handles service to service delivery using port numbers. Think of the IP address as the apartment building and the port number as the specific apartment number. Layer 4 acts like a receptionist directing calls to the right extension. In layer 4, we have two main players, TCP and UDP. TCP is the responsible child. It establishes a connection using a three-way handshake. Sync acknowledgement, and acknowledgement. It guarantees the delivery. If a packet drops, TCP notices it and resends it. This is great for emails where you don't want half an email. UDP is the speed demon. It blasts data out. It doesn't check if you have got it. If a packet drops in a video call, you just see a glitch for a second and the life moves on. That is why videos and gaming love UDP. Layer 5 is the session layer. It's like a manager of the conversation. It sets up meetings, manages the talking, and ends the call. If you're downloading a file and your internet blips, Layer 5 is responsible for knowing where you left off, so you don't have to start from zero. It also handles the traffic lights of communication, deciding who talks when, like half duplex versus full duplex. Layer 6 is the presentation layer. It makes sure that the data is in the format that the application can understand, is the translator of the network. This is where character encoding also happens, like ASCII. It's also where encryption and compression technically live. If you're sending a credit card number, layer 6 encrypts it so it looks like garbage to anyone sniffing the wire, but the receiver layer 6 can decrypt it back into numbers. We made it to the top. Layer 7, the application layer. This is the closest to you, but be careful. Your browser, like Chrome, isn't layer 7. Your Chrome is a software application and that uses layer 7 protocols like HTTP to talk to the network. The layer is responsible for actual requests like get me to this web page, send this email, or resolve this domain name like DNS. Let's trace a real request. You type google.com, the layer 7 creates a HTTP/HTTPS request. The layer 6 encrypts it. Layer 4 breaks down into segments and adds port 443. The layer 3 adds the IP address. Layer 2 adds the MAC address of your router. Layer 1 turns it into electricity. It travels across the world where Google server gets it. It reverses the process. Layer 1 reads the bits. Layer 2 checks the MAC. Layer 3 checks the IP. Layer 4 reassembles the segments, and Layer 7 finally hands the GET request to the web server software. The OSI model is actually a good theoretical model. The internet actually runs on TCP/IP model. TCP/IP is simpler. It squashes layer 5, 6, 7 into just one application layer because in code, developers usually handle the session presentation logic together. So why do we still need to learn OSI? Because it's distinct. When a vendor sells you a layer 7 firewall, you know exactly what they mean. It looks at the content of the message, not just the ports. So to recap, we move from physical bits up to global IPs, then to specific ports, and finally to the application on your screen. Hey, if this video helped you understand this topic, don't forget to like and subscribe. You can also drop your suggestions down in the comments about the improvements and the topics you would like me to cover next. Till then, thanks for watching, and I will see you in the next one. Peace.